Hello, everyone. My name is Tyler Thomas,
And my name is Mathew Piscitelli.
and thank you for attending our talk on the memory forensics of cryptocurrency hardware wallets. This is just a generic National Science Foundation disclosure. There's the grant number if you want to look it up.
So we are both going into our first semester of graduate school at the University of New Haven. We're also part of the UNHcFREG research lab, and we're members of the university's hacking team. We've done a couple competitions last year, including CCDC and CBTC, and in this upcoming year, we'll be doing a bunch more. So we're going to start off by talking about the problem we were looking at and why we were trying to solve it, what we contributed to the open source community, as well as what papers and previous work inspired what we did. We're going to talk about what we did, why we did it, and why we think it's important.
So to begin with, the series of questions that inspired this research centers around a scenario in which you're given a memory image of a computer that was recently running a cryptocurrency hardware wallet client. Now, with this memory image, can we detect the use of the client, of the wallet? Can we extract forensically relevant data related to the use of the wallet, such as the transaction history, public keys, wallet addresses, or other potentially de-anonymizing data? And if so, how long does those artifacts persist in memory, and how do they change over time? We have four main contributions with this work. The first is that we believe it's the primary account of memory analysis of cryptocurrency hardware wallet clients. We have shared our findings and the artifacts with the Artifact Genome Project, which is an open source digital artifact aggregation database hosted here at the University of New Haven. We have an open source tool for forensic analysis of the two clients we're going to be looking at in this presentation. And finally, we present a novel memory visualization framework for exploring the memory persistence of and integrity of artifacts across applications, not just within the two that are presented here. Quick literature review. Obviously, memory forensics has come a long way since 2004. Tools like the volatility framework have allowed for researchers such as ourselves to develop application-specific memory forensics plugins. Again, limited work has been done in cryptocurrency wallet memory forensics in general. There's a volatility plugin to regex for Bitcoin public keys on macOS systems. There are several tools for conducting file system triage and pulling files that have pertinent forensic information from Windows systems for a variety of different cryptocurrency clients. And finally, there is a memory forensics paper published that looks into the memory artifacts present are created by the network protocols that interact with the Monero blockchain, but that's a little bit different than what we're doing here because that's specific to a full node. The two clients we're looking at don't operate as full nodes. And again, there's no focus on hardware clients in any of this previous work.
So due to the anonymous nature of cryptocurrency, it's really difficult to find out the identity of an individual given only their wallet address. By design, it's designed to preserve anonymity of both the sender and the receiver in any transaction. So all the transactions on a cryptocurrency system are stored in a public database called the Ledger that anyone can view. However, you're not supposed to be able to figure out any information about any specific person based on that info. So because of this anonymous currency, it's really gained popularity with criminal groups in recent years. Ransomware especially, those syndicates have used it to extort payment from government organizations and other private sector organizations without being traced. I'm sure you all heard about the Twitter breach last week in which the perpetrators extorted over $100,000 of Bitcoin and because of the anonymous nature of Bitcoin, it's very difficult for law enforcement to figure out who's actually committing these attacks.
So the reason why we have this level of anonymity is because a lot of cryptocurrency wallets implement a technology known as hierarchical deterministic wallets. And what this means is that you start with a master seed and a master key pair that all other key pairs are derived from, and you begin to create this key of trees as we move rightward. And if you're able to move leftward up this key tree at any point, and you obtain a parent public key, you are able to de-anonymize all transactions that were created using that public key. because the wallet addresses can be deterministically derived from the parent keys. So our goal, one of the main de-anonymizing artifacts that we're looking for, are those parent public keys. So this is just a little bit of an overview of the security model of the hardware wallet itself. It's assumed that the machine that you are using the hardware wallet on is already compromised, and the client generates an unsigned transaction, sends it over to the USB device that is the hardware wallet, and it is cryptographically isolated. The private keys are cryptographically isolated from the presumed to be infected host, and the signed transaction is sent back to be sent to the blockchain, and the private keys never leave the device. So again, we're not attacking the private keys here. We're looking for de-anonymizing data.
So we took a look at the two biggest crypto hardware wallets on the market, being the Ledger Nano X and its respective Ledger Live client, and the Trezor Model 1 with its Trezor Wallet software client. So these are both similar in that they're leveraging JavaScript. However, the Ledger client is a standalone application built on Electron and leveraging Google's V8 runtime, while the Trezor client is in a web browser. We looked at it running Chrome and Firefox, and the Trezor, while being a web client, also includes a separate piece of software called the Trezor Bridge, which enables connecting the host USB device with the browser. So this is our methodology. So we examine memory a couple different ways. We started off by conducting exploratory memory analysis using Cheat Engine to look through memory events while they were occurring and to try to find these different artifacts that we were going to extract. Then once we had identified the structures, we wrote our volatility plugin to take postmortem memory dumps and identify and extract these different artifacts. And then we created a framework to essentially analyze and visualize all the statistics about these artifacts. So the right is kind of our thought process and our workflow. So what we did was we had a virtual machine running both these clients at different times. We would have a user interact with the virtual machine and carry out actions such as sending or receiving cryptocurrency or locking and unlocking one of these clients. And at every set interval, our tool would take a snapshot of the memory and run it through our volatility plugin, which would extract the different artifacts and export them as a CSV file. And after about an hour and about 30 different snapshots, that process would end, and then all those CSVs would be fed into our visualization framework, which would analyze the artifacts and give us our results. And these are all the tools and versions we use in case you're interested in that.
So here's an overview, a table with an overview of the data structures and their contents that we identified as forensically relevant. And because all of these applications, the two applications that we looked at were both JavaScript based, most of these take the form of JSON dictionaries. Specifically in the Electron app, we noticed that the segments of memory dedicated for inter-process communication were sending back and forth JSON dictionaries that could be easily retrieved and be in predictable locations. We also noticed that some of the data was embedded in HTTP requests in either URLs or in the request itself, and we were able to extract data from those. Here's an overview of our data extraction algorithm, and the main purpose of this, I won't go through every line, is to identify structures in memory using Yara scans, serialize the forensically relevant data structures from the memory dump and load them into Python objects in the volatility plugin, and detect and repair the structures that may have been damaged by memory smearing or deallocation, because these deallocation errors, these deallocation corruptions happened in predictable ways in predictable locations, and we were able to repair those JSON objects so that they may be serialized into Python dictionaries. And here's everything boiled down. These are the main things that we were able to get from each of the clients. For both clients, we were able to extract public keys, transaction history, past and future addresses, and unique device metadata. Now, what that means is that with this information, we would be able to de-anonymize all past and future transactions using these wallets and the private keys that are stored on them, as well as link that unique device itself to that computer. And also with the Trezor wallet, the application password was found in memory and in a predictable and extractable signature surrounding it. And here's an example output of the command line volatility plugin. In this instance, there's 3 public keys found and the beginning of one of the Bitcoin transactions related to one of those public keys.
In addition to the volatility plugin we created, we also created a visualization framework written in Python that will analyze all these different artifacts and then provide analytics and graphical data about them. So here's our main, basically what this visualization framework does is it'll calculate, are the artifacts intact? It'll figure out how long they're staying intact, and it'll figure out if they've been corrupted and whether or not they're usable by investigators. So here's kind of our main algorithm for calculating whether, like, how, what degree to which the artifacts are still intact. So it basically will, for each point in time and for each artifact, it'll take that artifact and compare it to all the other instances of itself across the timeline and figure out where changes have occurred in order to figure out if it's been overwritten or not. So to put that into a real picture, here is our experiment run on the Ledger wallet. So the first thing this visualization framework is going to do is show the number of occurrences of each artifact that are present at each point in time. So over the course of an hour, as different transactions were carried out, hundreds of instances of the extended public key became present in memory, along with dozens of instances of the entire transaction history. So those extended public keys are on top there, and the bottom, those objects are containing the transaction history. This is the same, so this is the artifact integrity. So this is different. So basically this part of the visualization framework is calculating how to what degree the artifacts have been overwritten. So for the Ledger wallet in particular, many artifacts remain completely intact and extractable throughout the entire experiment. So the blue and the purple lines are the public keys and the instances of the transaction history. And worth noting here, those objects were still present while the application was locked. And then even after the processes were killed, some instances of the artifacts remained in memory and completely intact, meaning they would be extractable. We ran the same experiment on the Trezor wallet and found similar results. So many instances of the extended public key were present and fully intact and had not been overwritten at all, as well as the application password used to unlock the client. That was also present in memory and fully intact. Worth noting here, even after the Chrome tab was closed, instances of both the passphrase and the extended public key were still present. And then even after Chrome was killed, some of these artifacts were still present. So we've demonstrated that even after the perpetrator was to close an application, for example, it still might be possible for an investigator to retrieve some of this information. The final component of our visualization framework makes it easier for the user to see how artifacts are present in memory and how they're changing over time. So in this example, with the Ledger wallet, the larger yellow squares represent the instances of the transaction history in memory, and the smaller red squares represent instances of the extended public key in memory. So if you were using this tool, it would be an animation, but I've shown a couple of static frames here, and essentially what it shows is over time, in each snapshot that we've taken, how artifacts are being created, where they're being corrupted, and how they are being overwritten. So what does all this mean? Essentially, we've demonstrated that we've been able to extract the extended public key from memory. So why that's important is because that can be used to de-anonymize transactions in theory. So like Kyle was talking about, we're moving left on the tree, where if we have the extended public key, we can derive all past and future wallet addresses, which are what would show up in the transaction. So if an investigator is able to obtain a public key and link that to an individual, they could potentially derive all these addresses themselves and find transactions that were created using these addresses, and then be able to identify the individual who carried out those transactions in turn. Additionally, many of these artifacts were present even after browser tabs or at the applications themselves were closed. So that's good news for an investigator who might not be on the scene until after the perpetrator has exited out to try to cover their tracks.
And to wrap it all up for future work, we believe that if you want to get a more robust extraction methodology for artifacts, not just in these two applications, but across all JavaScript-based systems, you need to get closer to the memory management system itself. To just do these signature-based scans is very time-consuming because you have to go into memory and look at how these things are organized and create byte-by-byte signatures that are prefixes and postfixes for the data you want to extract. And that could be very timely, and it's not very realistic to do that for every application. So if there was a generalizable object extraction framework for these different runtime environments, that would greatly expedite the forensic investigation of these applications. Finally, we'd like to acknowledge the National Science Foundation for the grant that funded this, the University of New Haven, the Volatility Foundation for creating the volatility framework and open sourcing it, as well as co-authors Ilya Shavrov and Ibrahim Baggili, and the UNHcFREG lab that we are affiliated with. Any questions?
Thank you for your time, everyone.